All right, thanks everyone. Good afternoon. My name is Jeff Foster. I'm a professor at the University of Maryland in College Park. And I'm really excited to be here to tell you about some work I've been doing for a while on adding some static-ish types to Ruby. So probably you're here because you're interested in Ruby, but just in case. So Ruby is sort of a combination of Smalltalk and Perl. And it's really popular for web apps. So Ruby on Rails is probably the main thing the language is known for. And the goal of our work, which we've been doing for a while, is to come up with a type system that adds sort of optional but useful types to Ruby. So this is sort of the normal kind of gradually adding type story. We want to be able to develop a program without types rapidly, and then add them later on slowly to get checking where you need to, so that you can find problems as early as possible in development. And sort of the punchline, which I'll tell you the reason for this partway through the talk, is that after doing this for a number of years, I think we finally have it right. I think we finally have a reasonable solution for a language as dynamic as Ruby that can add types to it. So what I thought I'd do first, at risk of screwing up, is do a demo. So the code for this system that I'm going to show you called RDL. Please don't ask me what RDL stands for because I don't actually know. It's up on GitHub, and there's a gem for it. Here's, well, you can see where I come on the VI Emacs war. So here's my Emacs buffer, where I've written this fantastic function, or method, sorry, called the answer, that returns a string 42, and that's it, right? So if I run this, it doesn't really do anything because I'm not actually calling any code, I'm just defining a method. And using RDL, what we get to do, if you want, is so we can load in RDL, and then we can enable annotations. And once we have annotations, we could say that my intention was that this method should take no arguments and return an integer. And I want you to type check this method right after it's defined. And if you do that, then when you load this program, you get this sort of catastrophic message, which if you look at the top of it has something interesting to say, which is that at this line 6, it got a string where type integer was expected, right? So this is one of the things that type systems is about. And you can think of this as adding redundancy, right? A little bit of redundancy into the program. So I don't actually know if the program is incorrect or if the type annotation is incorrect, but I at least know that they don't match, right? So somewhere there's a problem that I can find. So of course you can find these kinds of problems with test cases, but one of the nice things that you can do with a type system, so let's add an argument here, and I don't care what that argument is, so I'll just say it's any possible kind of thing. So let's say if x is true, return 42, otherwise return the integer 42. And the nice thing about this is if I run type checking on it, I get that type error again, right? But I didn't have to add any more annotations. So the one type error enabled reasoning about all the paths through the method, whereas if I was doing testing, I would have to write 2 test cases, right, to cover each of the 2 paths through the program. So that's one of the cool things about type systems, I think, and that's one of the reasons that I would like to add them to Ruby, is because I find myself, maybe I shouldn't admit this, but of course I make all kinds of mistakes when I program, and there are so many of those mistakes that I think would be caught by type systems that I want to be able to do that. All right, so let me show you one other sort of feature of this type system. So maybe for some reason I decide I want to return 42 as 1 plus 41. And if I do that, then actually I get a type error. And the type error is kind of odd. It says, well, there's no information for the instance method integer plus, right? So if you remember Ruby, everything is an object. When I'm doing 1 plus 41, I'm actually invoking the plus method on 1. And this is complaining that it doesn't know anything about the plus method, right? So the way this type system works is if you call out to other code, you need to provide some kind of type annotation for that. And there's actually a library of these things. So if you want to get those, you can load in the core library types. And if you do that, then this program will type check just fine. And those library types, of course, you can look on GitHub and you can kind of figure out what they are. But you could also query them with this command line tool. So here are all the types for the plus method of integer. I'll tell you what those sort of multiple types mean later on. Or maybe you just want the types of everything in the integer class, right? Or maybe, I don't actually know why you'd want to do this, but it was fun to implement, so I did. Maybe you have an integer and you want to get another one. So you just want a method that takes an integer and gives you one. So those are all those methods. Or maybe you just really can't think of an integer, but you have something else. So give me something that takes anything and gives me an integer. Well, they're all the things that do that. All right. So now I'm due to fear, I'm going to move on to slides because I don't want to risk any more demo. So my plan here is to tell you more about the sort of the types that Ruby offers and why they're interesting and why they're designed that way, and then tell you a bit about maybe some open questions at the end. And if you get bored during my talk, here are maybe a few interesting things to think about. So I said before, I want type systems to find bugs in my code, but there are all kinds of ways that types are useful. And one thing to think about is whether having a kind of type checking system, like the one I just showed you, is actually useful, right? So one of the main things that types help is actually even before you write the program is with design, right? So you get to write down, you get to think about the API of your program or your library or your methods or whatever, and the intermediate values of your program in terms of types, and it gives you a little bit of structure for thinking about them, right? So in fact, a long time ago, we did a user study. We were trying to check whether an earlier version of RDL was helpful, and we found we had actually kind of screwed up the user study because we made the problem too simple, and it was too simple in the sense that all the programmers who were carrying out the task we asked them to do knew that when they had x, it was always an integer. So they didn't actually need sort of the RDL type system because they just knew by name that if it's x, it's an integer, right? And that's because the program was kind of small. You can imagine in a bigger program, types are more useful with the design. Another aspect, aside from finding bugs, is that types are automatically checked, right? So this is kind of nice because, how often does documentation about code actually match the code, right? It's pretty much almost never. But the nice thing about types is that if they're checked against the code, you know that there's this sort of mechanical tool verifying that they match. So you can trust them. And in fact, we found, in doing the course of this project, we found a few places where the Ruby documentation doesn't exactly match what types are actually accepted by various library methods. And then finally, types are really useful for maintenance, right? So as a kind of dumb but really useful example, suppose you've got a method that you use a bunch of places in your program and you want to add an argument to it. Well, it's really easy to add that argument, and then if you have a type system, you know that the compiler or the type checker is going to tell you every single place you need to update to now call that method correctly. So that's like, I don't know about you, but when I'm programming Ruby without types, and I go to add an argument to a method, I get really worried, right? Because now all of a sudden, I need to know, did I actually remember to test every possible place that this method is called? And if the answer is no, I could have screwed it up. And with types, because there's sort of one type per method annotation, it's a lot easier. All right, so let me show you some of the kind of typing features that Ruby has, that RDL has, and explain sort of why it has them. And most of these examples are from type annotations for the Ruby core library. And the goal of all this was to come up with a type system that matches sort of the Ruby documentation and what Ruby programs do. So there's nothing in here that's added just because it's sort of intellectually nice, right? Everything is in here because there's some code that had a pretty good reason for using this kind of feature. And in the end, I think of this as kind of the kitchen sink of type systems. So there's really not any new kinds of types in the system, but there aren't many or maybe not any prior systems that just have all this stuff jammed together in one type checker. All right, so I showed you an example of this before, but RDL has basic types, right? So like this is a new annotation syntax. So before, the type annotation was just for the next method. This type annotation is for, the first line says, in the string class, the plus method takes a string and gives you back a string. The insert method takes an integer and a string, gives you a new string. And then finally, Ruby has lambdas or higher order methods or code blocks. So an example is on the bottom of the slide where the up to method is being called. So A up to Z iterates from A to Z and calls this code block with an argument C, passing one character or one string to that code block and printing it out. And as an aside, I don't really know why Ruby has this up to method. I can't think of any other use besides this slide, but it's in there, right? So, okay. And this syntax with the colon, if anybody doesn't know Ruby, that's just a symbol, which is an intern string. All right, so the last annotation up there is just the type signature for the up to method. All right. So we found that in RDL, we also needed union types, so ORs. So there's the code for the answer again. And suppose that the correct that it was actually the correct code and that the type annotation was wrong, and actually it should have returned either an integer or a string. So you can say that like you see on the slide. And so if you have something that's of type integer or string, or A or B, that means you can invoke anything on it that would work for both A and B, right? Because you don't know which it is. It's a union. So unions are kind of an interesting thing to have in a type system. They're really useful, but there's no exact consensus on the right way to add them, right? So different languages have different ways of doing it. So for example, C has actually a union keyword that lets you create untagged, unsafe unions of things. And that it sort of lets you overlap things in memory. That's the way a lot of C programmers think about it. But it's incredibly useful, so it's in there. In Java, you can do this kind of thing, but you need an interface, right? So if you want something to be either an A or a B, you have to think about, well, what method do I want to call in that? Let's say it's M, and then you make an interface having M in it, and then you say both of those things implement M, or implement the interface, right? So, so unions are useful. In RDL, we have them, and you can just create them on the fly using OR instead of having to name them or giving any separate identity besides just using them where you want them. And of course, wherever you have unions, you're going to have intersections, right? So in RDL, there are intersection types, and the intersections are restricted to being only at the very top level of method types, and they're used for overloading, right? So an overloaded method is one that can be called with different types of arguments, and it might return different types of results. So actually, maybe this is a sort of bad example because everything here returns a string, but the string slice method has many different kinds of things. You can either give it an integer argument to return one character, 2 integer arguments to return a range, and so on. So, so this is kind of surprising, right? Because Ruby does not have overloading, except Ruby does have overloading, as you can clearly see, because it's used all over the place in the standard library and in the core library, right? So what's happening is that Ruby, instead of having the compiler decide at compile time which overloaded method to call, it does runtime type tests instead. So we need to model that in RDL, so we have overloading. One really common use of overloading is for optional and variable argument types, or at least for intersections. So the chomp method of string takes an optional string as an argument. The delete method of string takes one or more strings as an argument. And you can see we have the question mark operator and the star operator, similarly to regular expressions, to indicate optional or 0 or more. And so those are really useful to have. And as an aside, one of the things that I discovered when I was building this type system is that I thought originally that in Ruby you would have required arguments first, and then optional arguments, and then variable arguments. Because that would make sense, right? Because then you could count to figure out exactly where the arguments went. But that's not true. So actually, you can have optional arguments in the middle of other required arguments. And all kinds of, you can sort of have whatever you want. So inside of RDL, it actually uses a non-deterministic finite automaton to try to do the matching so that that's possible. I don't know if I actually have the algorithm correct, but it seems to work most of the time. So the types so far that I showed you, they all use names, right? They're all nominal. They just refer to classes. And most of the time, I think that's what you want, but some of the time that's too restrictive. So for example, the puts method just prints something out, and it prints almost anything out. So I don't want to have to list every single class that puts could print because there's essentially an unbounded number of them, right? So instead, we can use one of these structural types where puts takes 0 or more arguments of some kind of object that has a 2s method that takes nothing and gives you a string. So that type makes sense, but actually there's sort of a deep philosophical question here that I don't know the answer to, which is when do you want to use nominal and when do you want to use structural types, right? So if you use nominal types, it's easy to understand, and the annotations are short, right? But they might not be flexible, right? Because maybe you're going to add another class in the future, and that class is not going to match that annotation, and then you're going to have to go change the annotation, right? Or you could do structural types, and it looks fine for this example, but some structural types are too big. Like, what if you have a method that takes something that could have a plus and a minus and a times and a divide and a modulus? I could write all that down, or I could just say the darn thing's an integer, right? It's much easier to say it's an integer than to give the full structural type, even though saying it's an integer is maybe not exactly precise. So that's a question I don't have the answer to, but it's something interesting to think about in the design of a type system for a dynamic language. RDL also has to have generic types because Ruby has arrays, right? So this is what they look like. So up here, we declare on the first line that array is parameterized by some type t. And then type declarations, like the declaration of push, says that it takes 0 or more t's and returns an array of t. OK, so that looks sort of straightforward. But what's interesting is because Ruby doesn't have types built in, once you have these generic types or these parametric types, it's hard to know what the type parameter should be without the programmer telling you. For example, here's an array 1, 2. I'm storing it in x. And I can't really tell without the programmer saying whether that's supposed to be an array of integer, whether later on they're planning to push a string on it. I just don't know, right? And there are sort of different ways to do it, but probably whatever choice you make, if you just assume that 1, 2 is an array of integer, that's probably too restrictive, and it's probably going to start annoying people. So what we do in RDL is we just require the programmer to annotate that. So if you don't put it, if you don't supply a type parameter, then RDL doesn't check. It actually allows any kind of contents. But if you want to, you can supply a type parameter. You could say that's actually an array of integer with this instantiate notation. And then if you try to push a string on it, then you'll get an error. All right. So and then one interesting twist on this is, of course, maybe 1, 2 isn't really an arbitrary sized homogeneous array. Maybe it's actually supposed to be a potentially heterogeneous thing of size 2. Right? So this is an interesting choice that a lot of dynamic languages make, right? So if you come from a C world, there's a dramatic difference between an array and a linked list, right? Because an array is like a contiguous block in memory. You can't extend it unless you get really lucky and there's free space after it and you can reallocate. Whereas a linked list, you can just allocate cells in memory and they could just be all over the place, but you can have the list be arbitrarily sized. And somehow a lot of languages, like Ruby, have decided, well, we're only going to have one kind of thing. And I don't care if it's slow some of the time, but we're just going to say an array can be arbitrarily sized, right? And you can use it in these two different ways. So RDL has to account for these two different styles of programming with the same thing. So here's a method f. It takes, in this case, an array with 1 and a string foo, and then it uses multiple assignment to assign the components to A and B. So if let's say that I just assumed, of course, without any annotation, I wouldn't do this, but let's say that we give this type array of integer or string using the union type. That's not going to be precise enough for this example because then A would be an integer or string and so would B. So instead, RDL has a special tuple type, right, which is the sort of natural thing with the square brackets here that says it's an integer in the first position, a string in the second position. But of course, maybe later on we discover that's false. So RDL has some sort of fancy footwork inside it so that when you write down an array literal, it assumes it's a tuple type. And then later on, if it decides that that was the wrong assumption, it goes back and it converts it into an array of the union of the tuple types and then rechecks that all the typing constraints are still satisfied. And it does the same thing for finite hashes, because hashes are also used as sort of heterogeneous and homogeneous containers depending on the application. All right, so there are more features in RDL, right? So there's a self type, right? You need that for things like clone, because if you inherit clone from a superclass and you call it, you're going to get an instance of your class, not of the superclass. And the only way you can get that to work is with a self type. It turns out you need singleton types too. So this is kind of a dumb example. So here, the real query method of integer, I'm indicating it always returns true. So maybe that's not very important to know. But it turns out that inside the type system, it's really useful to sometimes know that certain things are exact values so that when you branch on them, you know that you're only going to take one branch or the other. And that's particularly useful when there's code that implements overloading, and when it dynamically checks to see the class of something and then splits cases depending on the class. So because I want to support that, I want to have singleton types. And there's also some weird cases in the math library where like things return pi or 0 or things like that. So it's nice to be able to write those down. And then finally, we found it's as you'd expect, really useful to have type aliases. So here, %real is an alias for the union of integer, float, and rational. And so that's one way you can get sort of this interface style notation for things without having to declare one if you don't want to. All right. So so that was a really quick sort of dive through RDL. And actually, it took a long time to build this system. So this is it's kind of a funny slide. So every box on this slide is essentially either a paper or a piece of software or both that we built. And we started working on this, I guess I should be embarrassed, about 9 years ago. So it's taken this long to figure things out. And there's an edge from one box to the other if something sort of directly influenced the other. So we kept building different kinds of systems for adding types in Ruby. So we sort of came up with the type language reasonably early on. But then we tried, static things. We tried some things with profiling. We tried making things dynamic. And we did all this work on trying to get things to work for Ruby. But there was a massive problem with everything we had done that was sort of embarrassing, right? Which is this kind of example from Ruby on Rails. All right, so this is some code that I wrote for a website to keep track of talks, like the one I'm giving now, right? So a talk has a speaker, and it has a location, and it has an abstract, and a time, and so on, right? And in the system, a talk, so this is part of the model class for talk, so this was for Rails 4, so it extends active record base. A talk also has an owner, which is the user that creates the talk, and they're allowed to edit it afterward. All right, so and so there's this line here that says belongs to owner that indicates that a talk has one of the owners. And because the names of things don't quite match, I have to say that that's an instance of the owners is an instance of the user class. And then I wrote this fantastic one-line method, owner query, which takes a user and it just returns true if and only if the current owner is the user parameter. And that ridiculously simple method could not be checked by any of the previous systems that I had been working to develop. So all those boxes, the errors between them, they couldn't check this code. And the reason is that that method owner isn't actually defined explicitly anywhere in the program, right? There's no def of it anywhere. And that caused essentially all the previous systems to fail, right? So this is an example of metaprogramming. What's actually happening is that through some magic, when I call belongs to up there, it's actually on the fly creating, and I don't actually know exactly how it's creating. There's many ways to do it. It's creating the owner method, which I'm then using later on in the code. And this style of metaprogramming, it really permeates Rails. And because it permeates Rails, it permeates Ruby, because lots of people who program in Ruby, they look at Rails as a good model, which I think there are a lot of great things about it. And they sort of do similar things. So there's tons of metaprogramming in Ruby. And so it's not something that can be ignored, I think. All right. So what do we do to sort of solve this problem? Well, fortunately, what we realized is we could take all that stuff, and even though it didn't solve the problem, we could put together bits and pieces from the previous systems. We could take the type language we had before. We did some profiling stuff. That gave us the idea of running the code, see what it does. We did some stuff with runtime interception. We did some stuff with static checking. And we could kind of put it all together, right? So the reason I'm showing you this is not that I want to admit it took me so long to figure this out and that I sort of had so many, you could sort of call them false starts, but just to show you, we worked on this problem for a long time, like 8 or 9 years, and I'm going to tell you what we figured out, and it's going to take me like 2 minutes, right? And that's how we make progress, right? I mean, if it took me 8 years to figure something out, and then to explain it to you, it took another 8 years, we would never do anything, right? So anyhow, it's just sort of something to think about, because I do a lot of research, and I always think about it as, it's not trying to come up with a complicated idea. It's trying to come up with the dead simple idea that it just takes a long time to understand so that you can then build on that and do great things. All right, so what's the idea that I think was great coming out of this? Well, it combines two things. So the first is that type annotation that I said was an annotation is really just a method call, right? So I didn't put the parentheses around it because you don't have to do that in Ruby, but it's just a method call at runtime. So when I say, type string, et cetera, all that's doing is storing in some global table a mapping from saying the string slice method has this list of types. So they're just a global type table. And that's why I could do that funny thing with RDL query. All that's doing is loading up the Ruby environment. It's loading in the types, and then it's just going through that table and spitting out the data, right? So these type annotations are method calls. And then we can do static type checking against those types, but we can do it at runtime when stuff has been loaded. So, so that call up there where I said, I guess this doesn't quite match before, but so foo has type integer to integer, and I say type check now. What that's doing is it's when the method foo is added, it sees it has the type check now annotation, and then it's grabbing the source file, parsing it, finding the foo method inside it, and then doing static type checking against that global environment, which has all the types that came before it in time, right? Now, that's actually kind of useless, except in demos. You don't usually want to type check things right after you define them. For example, mutually recursive functions kind of don't work that way. But a really good way to do it is you can just put some label on the type check annotation. You can say type check at label, and then you can do type check at that label sometime later. And so that lets you actually turn type checking into a test. So you can write a test case that when you execute it, just type check some chunk of your program, right? All right, so now that we have that feature, we can solve the metaprogramming problem. I have to do a very quick aside just to show you some notation. So in addition to the static stuff, RDL also has some dynamic stuff. So it also has contracts in it, and it lets you check pre and post conditions. So, so here's a line. Here's an example where we have some foo method, and we have a precondition that its argument x has to be greater than 0. So if you put that annotation on and then you call foo of -1, you'll get an error that you violated the precondition. And you can also have a post condition, which is similar right down there. All right. So when you have that pre-call, we can abuse it to intercept the belongs to call and create type annotations on the fly. So now, of course, when RDL takes over the world, this will just be part of Rails. But until it does, we have to sort of tack it on afterwards. So the way we do that is, so we add a precondition on belongs to. So we're doing this purely for its side effect, not to actually check any conditions. We're going to take the same arguments that, that belongs to takes, which is the name and the options. And then we have some code that creates the type annotation. So if options exists, then class strings is options of class name. Otherwise, class string is name.singularize.camelize. So that kind of crazy string manipulation is really not something I would want in my static type system, right? Like Rails has an internal table that has singular and plural versions. It knows exceptions, like it has the plural of octopus is octopi. I don't want that in my static type system. I'm sorry, that's just too messy. But it's perfectly sensible to have in runtime at Rails when the entire Rails environment is loaded and it's a trivial call, right? And so once I have that, I can then sort of do the computation, and then I can call type to create the type annotations. And so now that belongs to call, whatever kind of wacky thing it's doing to create the owner method at runtime, I'm just also having it create the type annotations at the same time, right? Which seems perfectly sensible. If you're going to go to all the trouble to create a method at runtime, it's really not much more trouble to create types for it as well. So now all of a sudden, this method that looked dead simple, that should be really easy to type check, as long as you have the right annotation for belongs to, it is really easy to type check. And that, I think, is the key idea that really has enabled us to apply to Ruby and to Rails code for real. So, so like I said, this approach, it works with all kinds of metaprogramming. Doesn't matter what the exact implementation is. The efficiency is probably not too bad because the metaprogramming code, you're not going to do metaprogramming in a tight loop, right? You're going to do it kind of at the outside, which means the type annotations are not going to be in a tight loop. They're going to be on the outside. And if you want, you can disable all this stuff in production. So there's an RDL disable module you can load instead of RDL, and that's just going to cause all the type annotations to be no ops. In Rails, there's some stuff for RDL so that that will be done automatically in production. I don't want to say that Rails support is bulletproof. It's still kind of sketchy, but the core ideas are there. All right. So that's most of what I wanted to tell you. Let me wrap up with just sort of a few high-level things that I don't know the answer to that are maybe worth thinking about. So one question that anybody who designs one of these type systems for a language that doesn't already have it has to answer is, should the type system be sound? Meaning, should it be the case that if the type system accepts a method, in this case, then the method will not have any type errors at runtime? So one example of this question comes up with generics, right? So here is a method f that takes an array of integers, and then it passes that array to g, and g takes an array of anything, and it prints out the array, and then it returns, and then inside of f, we return x sub 0 plus 1. All right, so it's just some nonsense code. So should we allow that? Well, it looks okay, and this kind of code would actually be allowed in Java, right? But there's sort of a standard type soundness problem here because arrays are mutable. So if instead of just printing out the array inside of G, if I had actually messed with it, like here I've changed x sub 0 to be this symbol foo, which I should be allowed to do because G takes an array of any, so it should be allowed to change it to anything, then I'm going to get a type error inside of f when it returns, because now x sub 0 can't be added to 1. So like I said, this is a standard problem. We have two names, x and y. They both refer to the same data structure. They have different types, and that data structure is mutable. So there is a trade-off. There are different answers to this, right? So the first example adds flexibility, and it adds fewer complaints. It has fewer complaints from the developer, right? So Dart does this. It allows this because sort of the goal is to find bugs and not really get in the programmer's way. But on the other hand, if we don't disallow the second example, then there could be bugs in the program that we don't warn the programmer about. And I don't really know what the right answer is. This is one of these cases where there's not a clear consensus, right? So there are lots of languages that have done different things, and this is not like static typing, or static scoping. So basically, every language has agreed that static scoping is the right choice. There are sometimes you want to use dynamic scoping, but not that often. So static scoping is the default. This is not so clear. The jury is still out of it. What about if untyped code calls typed code, right? So here's the f method. I've annotated with integer to any. Let's assume that I've type checked it, even though I haven't put in the annotation. So now I have this wonderful method. I've done fantastic type checking. I know there aren't going to be any type errors. And then I have some untyped code that I didn't check, and it passes a string in, and then it violates the whole type annotation and just blows everything up, right? So that's potentially a problem. So we can solve that problem in RDL by adding this wrap annotation. So if you set wrap to true in the arguments of type, it will actually treat the type as a contract, and it will dynamically enforce that the argument has to be an integer and the result has to be any. So that's good because it helps soundness, but it's bad because it adds runtime cost, and it means your production code might fail. So again, this is one of these sort of sticky issues where there's no clear answer one way or the other. All right, so I mean, in general, I think it's really interesting to think about when types are a good fit for your program, right? So when is this kind of system going to work? So it's going to work well. This is going to sound a bit like a tautology, right? When the code is mostly typable using the system, meaning if it's typable using standard reasoning, right? So the examples that I showed you, they type check pretty well. But if if you have code where you say, well, this argument is a string, except on the third Monday of the month, if it's a full moon, then it's an integer, that code is not going to type check using any reasonable type system, right? So that kind of complex reasoning is not going to be amenable to typing. On the other hand, if we made a type system that could do that kind of reasoning, maybe it would be really hard for the programmer to predict. So maybe the type system wouldn't be as useful, right? So one of the reasons types are useful, I went back to the idea of design. If you can't predict whether the type system will accept your program or not, then it might be hard to internalize that model of type systems and use it to help design your program. So that's a really interesting trade-off. And going with that, you have to be willing to write down type annotations to use this system, right? So we are doing some work on type inference, which would lighten the burden. But at some level, you have to be willing to annotate, which means your code has to be in a reasonably stable state, right? Because maybe if you're furiously changing things all around, you don't want to have to also change the types as well. And you have to be able to use the kind of types that are written down without the annotation burden being too high. So for example, if you have heavy reliance on Ruby's something that's called duck typing, usually I call it dynamic typing, and you want to use structural types everywhere in your program, well, that's going to be a lot more effort to do, right? So you may not want to use RDL in that circumstance. All right, so that's most of what I wanted to tell you. Let me give you a quick status report. So we're working on making this a more robust type system. We've gotten some interest from industry, and we're getting some pull requests on it, so that should help make it more bulletproof and easier to adopt, I hope. We're looking into additional features to it, like being able to serialize that type database so that you can do more stuff online. I can envision implementing some actual overloading with it, which might be fun, better handling of certain features of Ruby like method missing. And then on the research side, we're looking more into type inference. And there the challenge is we want to be able to provide useful types to the programmer, which is actually hard because usually type inference systems infer structural types, which turn out to be big and complicated and incomprehensible in practice. And we're also looking at verification. So can we actually prove properties that are deeper than just types? All right, so that's RDL, this type system we've developed for Ruby. And I think the punchline here is that to get it to sort of fit with this dynamic language, the key insight is doing static type checking, somehow static, but doing that at runtime. So still being able to reason about all possible paths through a method, but doing that reasoning at runtime after metaprogramming code has been executed. And it took us a long time to figure that out, but now it seems completely obvious to me that that's the right way to do this. The latest version of RDL is available. It's on GitHub, and there's also a Ruby gem. Try it out, and let me know what you think. All right, thank you. We have time for a couple questions. Yeah.
Excuse me. So, big thing, experience with my Ruby code is method will typically either return a useful result or nil, and so other languages deal with that monads and things like that. That obviously doesn't seem practical on a widespread basis in Ruby, but is there a way that you propose dealing with that?
Yeah, that's a really good question. So the question was, what about things that either return a useful result or return nil? And my answer was to punt, because actually there's been a lot of research on building type systems and other kinds of program analyses to try to reason about null pointer errors, right? Whether something could be null later on. And based on looking at all that work, my conclusion was that it's not really so simple to do, and that if you actually try to treat nil differently and not allow nil where other classes are allowed, then you're in for a world of hurt as far as the annotation burden for programmers that didn't design their program with that in mind. So we just punted that and did the usual Java, C, et cetera trick, and nil is just a subtype of every other type in the world, and so you can use it where those other types are. So you can still write the annotation. So a lot of the standard library methods are decorated to say they return class A or nil, so that you can still see that. But when checking the types, we don't check for nil. We just allow it to appear anywhere to just sort of get out of what I think would be a very hard system to use. Yeah.
Sorry if I missed this, but what about interfaces or mixing modules? Can you specify that the parameter needs to be enumerable or?
Yes. So there's so for mixins, you can definitely say that something is an enumerable, and then it will check the type of the against the enumerable annotation, just right. So if it's an enumerable, it will just look at the enumerable type signature and it will just pull types from that, and it will work just fine. The one thing that I'm not sure if we support in the implementation yet is if you're actually type checking a mixin, and the mixin calls out to something that's not defined in the mixin but will be in the class that it's added to, I don't know if we type check all that correctly. We actually have that. We're working on the verification part, and we have that for verification, but I don't know if we ported it into RDL yet. But if not, that will be coming soon. Yeah.
Do you think that the whole gradual typing thing is going to be like a really big thing? Because I think that's still kind of a, at least in industry, still kind of a unanswered question. Like, obviously, it's your work, so no bias. But what's your take on that, I guess?
All right. So what's my take on gradual typing? So that's a good question. I don't know. I mean, I will say that this system does not do the full gradual typing thing of wrapping untyped code so that if you call into it, you can blame the right party. And I'm not doing that because I think that the runtime burden would be too high. So like I said, we built some previous fully dynamic checking systems for Ruby, and we found that it was just way too expensive. Like, everything slowed down way too much. So I didn't do that. So I guess I think that it's sensible that you would want to be able to add types to these languages and both write code without types and write code with types, and maybe want to switch a little bit between them. But I don't think we know exactly what the pattern is, right? So for example, one pattern could be all your libraries have type signatures, and then your application code doesn't, and you use the type signatures for the libraries to, instead of like soundly enforcing types for your applications, to do more like squiggly underlines in your IDE about things that might be suspicious, or to give you code hints for completion or something like that. So that would be one design point. And then I think another one is just people just saying, we're just going to always use types, right? I mean, I think in practice, if you want your program to be typed, you kind of have to design it that way from the start. But I think that the reason RDL works for a lot of code is that people do, right? So like, even though Ruby has dynamic types, because maybe everybody has been so brainwashed, or maybe because it's a better way to design programs, people tend to write their programs in a typed way anyhow. So maybe gradual typing is more about giving people a way to just reduce the annotation burden at the front, but not really to change the way that they program. So I haven't really given you a good answer, but it seems to me that what industry is actually aiming for with all these gradual type systems, and what researchers are aiming for, is really just type systems that are going to be there. And is it just the right type system for the program? And probably there's not going to be, I think if people find the right type system, there may not be that much gradual about it in the end. We may wind up just programming with types most of the time. All right, well, again, thanks very much for your attention. I had fun. I appreciate you being in the audience. Thanks.